Hello and welcome to yet another riveting video. We're going to talk today about titration curves. Pretty fascinating way of tracking what's happening in an acid-base titration from a graphical and kind of visual perspective. So if we're essentially tracking pH as a function of added either acid or base, what we're going to find is that we're going to see some pretty interesting changes here. Generally speaking, if we add a strong acid plus a strong base, or we look at the reverse, a strong base plus a strong acid, and I'm generally using the sort of convention of whichever one I'm writing second here will be the one that we're adding to the one that's listed first. So if we did that, you get fairly standard looking kind of graphs as we do this. So if we add a base to an acid, of course with an acid the pH will start low down here somewhere. If this is my y-axis, on the x-axis we're going to have milliliters in this case of OH minus that we've added. Over here milliliters of acid that we're going to add. And so back to our first graph, if we're starting with an acid and adding a strong base, the acid will keep the pH pretty low for a while, and then you will note that it goes up very quickly and then sort of levels back out. With the reverse situation, starting with the base, the pH will start up high, look kind of similar, won't change a whole lot, and then it'll suddenly drop off and then sort of level back out like that. So those are fairly consistent kind of things. One thing to note, as the graphs sort of have these logistics or log functions to them, which makes sense because pH is a logarithmic function, you're sort of putting two of them back to back. The negative log of H plus and then 14 plus the log of OH minus sort of being put together to different places. And that sort of inflection point almost is where you've added equal amounts of the two. So if I've added equal amounts of acid and base, then I get what's called the equivalence point, which we've mentioned briefly in the previous video. And the equivalence point then is when I've added equal moles of OH minus and H plus. And rather interestingly for these, that means the pH is 7. And that's because the acid and the base are equal in strength. And because they're equal in strength, they react with one another, producing water and a salt. And the salt that they produce is not one that's able to have any impact on H plus or OH minus. And so the pH remains at 7 when you've added equal moles of acid and base. Now things get more interesting when we're talking about what if one of the acids or bases is stronger than the other. So if we have a weak acid plus a strong base, if we have a weak acid and a strong base, again, we're going to be tracking pH on the y-axis, and in this case, milliliters of OH minus added. The pH will again start low, not maybe as low as it was before. There are some interesting changes. One, the pH kind of comes up a little bit more instead of staying flatter, which we'll talk about a little bit more. It still does go through that steep rise and then levels out again, much like the other graph did. So let's talk a little bit about some of the differences here. So the first difference is indeed this rise. So the pH rises. Why is that? Well, the pH rises here more than the other one because at any point when the strong base has been added to the weak acid, there is a conjugate base being produced. So the production of the conjugate base, let's call it A minus, raises the pH. So in the previous example, whatever conjugate base we may have had was part of a strong acid, and a conjugate base of a strong acid like Cl- or NO3- has no impact on pH whatsoever. It doesn't stick to H+, so it doesn't affect anything, so the pH stays pretty low. So, in that example, you would have a pH that, would look a little bit more like this at the beginning, and we don't have that anymore. So we don't see that difference here simply because the conjugate base, again, is itself a base, and therefore causes the pH to go up a little bit. Let me get rid of those. The other interesting sort of point here is that this inflection point, again, in this case, will occur above 7. So it's higher than 7 in all cases here with a weak acid and a strong base, and we might want to know why that is. So pH above 7 at the equivalence point. Why? Well, again, what's left at the equivalence point, we'll talk about this more in just a moment, what's left at the equivalence point, there is no weak acid, HA, there's none of that left anymore. There's no OH- anymore. They've reacted with each other perfectly, and when they react with each other perfectly, what you get is water and A-. And A- is indeed a conjugate base. And because it's a conjugate base, when it's the only thing floating around in water, because all the OH- and all the HA are gone, then the only thing that can affect the pH is A-. And because it's a base, the pH will be higher than 7, because as a base, it will raise the pH. So the presence of A- raises the pH. Now, a couple of key ideas here that are certainly well worth knowing, well worth discussing, and we'll talk maybe more about a particle diagram understanding of this in a future video. I want to kind of just go through the different parts of this curve. Kind of think about what's going on in this graph here. So at different points, we'll sort of go ahead and label 4 sort of points. There's one point here which we'll label A. There's sort of a region here which we'll call B. There's that equivalence point, C, and then another region, D. So points at A and C, regions at B and D. At point A is simply the weak acid all by itself. And the one thing that there is a lot of at this point, because it's a weak acid by itself, there's lots of HA and not much else. So there's HA floating around in water. There's very little relatively H+ or A- or anything else. So that's our predominant thing. In region B, we've started adding OH, but there's still more HA than OH- at this point. And because there's more HA than OH-, all the OH- will react. It's the limiting reagent, so it's going to go away. And there'll still be some HA left. But when they do this, they produce A-. So at all points in B, there's a mixture of HA and A-. And that ratio of HA to A- increasingly favors A- as you go up the curve. So as you go up the curve, there is more A- and less HA. And again, because A- is the base, HA is the acid, as you get more A- and less HA, the pH gets more and more basic. At C, again, we've talked about C. C is the equivalence point, so you've added equal moles HA and OH-. And when you've done that, they react completely with each other, so they're both going to be gone, and you only have A-. So at point C, the equivalence point, you only have A- floating around in any appreciable amount. And then region D, Sometimes I call that Beyond the Sea. Maybe you're familiar with the Bobby Darin song, Beyond the Sea. Somewhere beyond the sea. Look it up if you don't know it, because I'm sure I did a great rendition. Beyond the sea in region D, you've now added more OH minus than HA, than you had HA. So all the HA is gone, and you're going to have some leftover OH minus, and you also did make a whole bunch of A minus along the way. Because the A minus that you made all along the way is still there. It just so happens, of course, that OH minus is, thousands and thousands or millions and millions of times stronger than A minus, because it's a strong base and A minus is not a strong base. So the pH is really a function of OH minus, which is why the curve looks a lot like the strong base curve, simply because you have so much strong base relative to the weak conjugate base A minus. So it might as well just be the OH minus by itself. The A minus, from a mathematical standpoint, is irrelevant. One last thing before we move on from this curve and talk about a different one. There is, again, an interesting point somewhere in region B, which is halfway to the equivalence point. So whatever our halfway to the equivalence point is, this volume here, if I get halfway there, this is the half equivalence point. And at the half equivalence point, when it all shakes out, we've talked about this before, the amount of A minus equals the amount of HA, and that, again, is of mathematical interest, because at that point, then pH equals pKa, or as we might say, H plus equals Ka. That's a very interesting point, and mathematically a very useful and easy point from which to do some calculations. So something to kind of know and appreciate as you go on. Okay, let's say that we turn things around and add a strong acid to a weak base. We'll kind of breeze through this one because it's a relatively simple concept if we understand the first concept fairly well already. So if we have a weak base plus a strong acid, we have, again, pH, in this case, though, not milliliters of OH minus added, but milliliters of H plus. The pH starts higher and, again, drops a little more gradually than it did before, and then sharpens out and then levels out again. It wouldn't backtrack, obviously. That's not a particularly good function, but you guys know my artistic skill, very limited. So, again, we have this situation where the pH is dropping. Here, the pH is dropping, as we know, because in this particular case, if we consider the weak base to be B and H plus to be the strong acid, the pH is dropping as the conjugate acid HB plus is produced. And that conjugate acid is going to lower the pH. And so even though all the acid, the strong acid H plus, is being used up, it's a limiting reagent, this production of HB plus is going to cause the pH to drop. And then, of course, we have this situation where we have the equivalence point here. Again, in this case, the pH would not be 7. It's going to be less than 7. And the reason for that, again, is that at the equivalence point, all the B and H plus have reacted with each other. They're both gone, but what they've turned into is HB plus, the conjugate acid. So this conjugate acid is really the only thing floating around in water of any appreciable amount at that point. And because it's the only thing really floating around at that point, because all the B and H plus are gone, the pH would be slightly acidic as a result of its presence. And so those are the two key points to note in a curve like that. If we were to, again, sort of, in this case more briefly, I'm sure you're glad for that, were to break down that graph in terms of the 4 regions that we talked about before, again, we would talk about pH, milliliters of, in this case, H plus added. The curve, again, try to do a slightly better job this time. I don't know why it took so long for it to be neutralized that time, but again, me and Art getting along great together. So again, if we look at the 4 points we sort of have here, we'll call this W. We'll call this sort of region X. We'll call the equivalence point Y. In this region, we'll call Z. So at W, we have just the weak base. So the main thing floating around in water there is just the weak base itself. So that predominates. And then in region X, when you started adding H plus to that, there's still more H plus. No, excuse me, let's back that up. More B than H plus. And when there's more B than H plus, all the H plus is going to go away. So you're going to have some B that's left. And you also, don't forget, produce HB plus. And so there's some of each. So you have both B and HB plus floating around in water. Because the more H plus you add, the more HB plus you make, there is more and more HB plus as you go down the curve. And so as you get closer and closer to the equivalence point, the reason the pH is dropping so much is that you're running out of your weak base, B is going down, and your conjugate base, HB plus, is going up. At point Y, the equivalence point, you have equal amounts. So you have equal B and H plus, and so they're both going to be gone. They've reacted with each other perfectly, and they're both gone, so you have only HB plus floating around. And that's why, again, the pH is acidic, because it's a conjugate acid, and so the pH would be below 7 as a result. And then region Z, beyond the Y, doesn't really have quite the ring to it that beyond the C does. No songs written about beyond the Y, as far as I know. But in region Z, when you've overdone it, you have excess H plus. That excess H plus is going to be there in addition to the HB plus that you made along the way. So you have two acids, but again, the H plus is thousands or millions of times stronger than HB plus. So the presence of HB plus from a pH perspective is not very important. From a particle diagram perspective, we should know that it's there, but from a pH perspective, not all that important. And again, last but not least, if we had, this is our equivalence point volume right here. Halfway to that point would be the half equivalence point. And that half equivalence point, the half equivalence point would indicate that once you've reacted half of your B, you have equal amounts of B and HB plus, and in the K expression they would divide out such that your PKB would equal POH, or simply that KB equals the molarity of OH minus. And again, an interesting thing to consider there. What we'll probably do in the next video, there's a Khan Academy video that I'd like you guys to watch that talks a little bit about pH indicators. I'll probably go into the background of indicators a little bit. I'm a little surprised they don't talk more about the background of it. I think it's actually pretty interesting. It's a very Le Chatelier's principle thing. So we'll talk about pH indicators a little bit, and then we'll talk about particle diagrams and all this sort of stuff and how that would work. Because again, I think that's a pretty interesting way to think about the topic. So, but that's it for today. Maybe watch this again, maybe double down on it, make sure you understand this idea. This is a very important thing. In the old days, the College Board did a whole lot of math with this. That's not really the case anymore, even before the corona cancellation. But it's still a good idea to understand the concept of all this stuff. The math is pretty crazy, and luckily we don't have to do much of it anymore. All right, signing off. We'll talk to you guys tomorrow.